Hello everyone. We're going to begin chapter 5 now, which is going to be on continuous probability distributions. To begin with, we're specifically going to be focusing on the normal probability distribution and the standard normal probability distribution. So before we begin, let's talk about some differences between our discrete probability distributions, which we've covered previously, and our continuous probability distributions. When we had our discrete probability distributions, we talked about specifically what is a probability distribution. And a probability distribution was just every single outcome and its associated probability. So when we first introduced probability distributions, we had this sort of definition. This would be, for example, if you had a frequency table where you have your frequencies and you have your outcomes, and then you would have some outcome, whatever they would be, the number of frequency, and then from there, you could figure out what the probabilities were, or relative frequency, and you would get your probability distribution, the probability for every single possible outcome. Then we also looked at the case, though, using discrete probability distributions, where we had a formula that described every possible probability from any given input. This would be for cases where you have a ton of different possible probabilities based on the number of outcomes, or sometimes even if you have countably infinite number of possibilities. Now, for a continuous probability distribution, this definition is pretty much out the window. There's no way that you can list every possible outcome and its associated probability because there's an infinite number of outcomes, which means that there would be an infinite number of probabilities. For the discrete case, we actually had a name for this, which was called a probability mass function. And this is the function that describes possible probabilities for every single possible outcome. So this is referred to as a PMF. For our continuous probability distributions, we actually have what's called a probability density function, or a PDF, which describes every possible probability given some input from our infinite number of possible inputs. So the probability density function is a function that is used to compute probabilities of continuous random variables with the following two properties. The first is that the graph of the equation must lie above the horizontal axis, and the area under the graph must be 1. So regardless of what sort of continuous distribution you have, these two things must be true. It must be 1 above the horizontal axis, and 2, area is 1. So just to give two brief examples of what this might look like, the one that we're going to be looking at in this chapter is you have a normal distribution, which would look something like this. It's a bell-shaped plot, and notice that it's above the horizontal line, and this entire area would be 1. Or another example you might have would be something like a uniform distribution, or something like this, where you have some A, some B, and it's the area underneath this curve, which in this case is a straight line, because in a uniform distribution, all outcomes are equally likely. So the area under this curve would be 1, and it is at or above the horizontal axis. Let's talk about the normal distribution. A continuous random variable is said to be normally distributed or has normal probability distribution if its corresponding relative frequency histogram has the shape of a normal curve, or that is a bell-shaped symmetric curve. So to draw a normal distribution will look something like this. You have your horizontal axis, and then you have this bell-shaped plot that goes over it like this. And notice it specifically says the relative frequency histogram. And we'll talk more about that when we get into normal approximation and things like that for other distributions. But for now, just know that it is a bell-shaped plot that is above the horizontal axis. And this is actually often called a Gaussian distribution or Gaussian plot, named after Carl Gauss. Now, this normal distribution has two important features. The first is the mean mu. This is going to be the location of our normal distribution. That is the center point. So if we have this bell-shaped curve, it is going to be centered at mu. This tells us where in positional space is this actual distribution located, where is its center. The other piece of information is the spread, which we use standard deviation for. So this tells us where it's located and how dispersed this distribution is. So for example, if I have a similar normal distribution, but maybe I shift it to the right, I can do this by just changing mu. Mu is telling me where, if I have a number line, where is the center of my normal distribution located? It actually tells us physically where is that normal distribution. The standard deviation tells us how much dispersion there is in that distribution. So for example, I could have the exact same plot here, but instead I might have it look something like this, where maybe it is less spread out. Or I may have a similar plot centered at mu, but maybe it's more spread out. All of these would be normal distributions which are centered at this point mu. They're in the same position, but they have different spreads based on this standard deviation. So in general, the way that we're going to refer to a normal distribution is we'll write it like this. Capital N for normal, mu sigma. So these are the two important pieces of information that we'll need. Now, I do want to point out in some textbooks and things like that, people will actually use sigma squared. So you may need to check with what convention the source is that you're using. But this is the one that we're going to be using for this course. So for example, if I wanted to have a normal distribution that's centered at the point 21 with a spread of 3, it would just be N 21, 3. And this tells me that I have a normal distribution with a mean of 21 and a standard deviation of 3. Now, a couple things about this normal distribution, because remember, this is continuous. So if you had a number line, it goes from negative infinity to positive infinity. This means that on our normal distribution, what's happening is we have our bell-shaped curve centered at mu. We have some amount of spread based on the standard deviation, so let's kind of draw it like this. And what's happening is as you go to the tails, they're getting closer and closer and closer and closer to that horizontal line, but they will never touch. They will approach it asymptotically. And the range of these x values, because that's what this horizontal axis represents, your x values, the range of this will be from negative infinity up to infinity. So even though it becomes less and less and less likely as you go further to the edges, it is going all the way from negative infinity up to positive infinity. And that's what this graph actually represents. The area under the graph is a probability. We'll talk more about this when we actually get to calculating probabilities, but I mentioned it previously that we're not going to be able to find the probability for a single point. What we're going to be doing is we're going to be finding the probability of some interval on our normal distribution. And this area between those values is your probability of that event occurring. As I mentioned earlier, our normal distribution is going to be centered at the mean mu, where the highest point is going to be right above this center point. Well, if we look at previous things we've looked at for central tendencies, we looked at 3 of them: mean, median, and mode. And mode was described as just what occurs most often, which would be associated with the highest peak. So for a perfectly symmetric bell-shaped curve, the center point, which is the mean, would be equal to the mode. This is also going to be equal to the median, because again, this point is the center. It's symmetric about the left and the right, meaning that there's just as much data to the left as there is to the right, meaning that this point, the central point, is also the median. And then of course, because this splits the data in half, again, it's symmetric, half the data is to the left, half the data is to the right, it is the mean because for every bit of data to the left, there's an equal and opposite amount of data to the right. So when you have a bell-shaped curve that is perfectly symmetric, your mean equals your median equals your mode. Now, previously, we did mention that median oftentimes will be a better central tendency when you actually want to look and describe data. We want to find out where the central point is because mean can be highly affected by outliers. But mean is a lot easier to do calculations with. There's a lot of things that mean is just more convenient for. Well, with central tendencies, specifically for the normal distribution, mean equals median, which means that we actually get the strength of both because they're equal if you have a perfectly normal distribution. Now, it is not to say you will always have a perfectly normal distribution. For example, we talked about this previously, but if my distribution is shifted and I have my tail going out to the right, where I have what's called a right skew, in this case, my mode would still be where the peak is. My median would be shifted somewhat to the right by all of these values that are being over here. So this would be maybe over here. And of course, because the mean is highly affected by outliers, my mean would be further to the right, so it'd be greater than. If I had a left skew, then again, my mode would be where the peak is, my median would shift slightly to the left, and my mean would shift even further to the left. So this is for when we have left skew. But oftentimes we're using this principle right here when we're looking at normal distributions. We want to have as little skew as possible. The closer it is to perfectly bell-shaped and symmetric, the more this will be true. So the curve approaches our horizontal axis. It's asymptotic, that means it will never actually touch. But the area under the graph is 1. So when I have my normal distribution, remember, the area of the graph represents the probability. And we talked about in chapter 3 that our probability of all possible values must be 1. It's the same thing here. Now, where it's a little bit different is previously when we would look at something like the probability of the sample space being the sum of all of the different probabilities of X, especially if they don't have any overlap, things like that. Well, in this case, because we have continuous data now, we can't take the sum of all the possible probabilities because there's an infinite number of them. So we're actually going to do, when you're finding a probability, is you would use the integral from, in this case, negative infinity to positive infinity, and then we have our function which describes this normal distribution, dx, and this would be 1. And any time we're taking a probability between two values, we would just take the integral from a to b for f of x dx, and this would give us the probability associated with that. Now, for this course, we don't assume that anyone's taken calculus and knows how to do this, so instead we're going to be using a table to approximate all of our answers. But there is one key aspect that I want to kind of bring up to show you why we're not going to be finding the probability for one single value. So let me clean this up and then I'll show you why that is. On our normal distribution, remember that this is continuous, meaning that there's an infinite number of x values on this line. So let's say that we wanted the probability of this exact x value. Well, this would be represented by just this line, which has absolutely no width to it. So whenever we try to take the area of it, width times height, there's no width. So it's basically just whatever height times 0. Or if you wanted to treat it as the integral we talked about, you'd be going from some point A to the exact same point A, f of x dx, which this, of course, in calculus, if you've taken the course, you would know this. If you haven't, just know that this would always be equal to 0. This means that the probability of any specific outcome from a continuous probability distribution will always be equal to 0. Now, it's not actually equal to 0, right? Even if I have an infinite number of possible outcomes, if I tell my computer to randomly pick one of them, something is going to be picked, right? So it's not actually 0, it's just infinitesimally small. So it's infinitesimally small, which means that it's a value that's so tiny that we just say it's 0. It's like 0.00000, and it's just on forever. It's super tiny. So for all intents and purposes, though, the probability of if I have an infinite number of possibilities would be 0. Let's try to put it in context of what we did in probability. When I asked you to find the probability of a point x, it was the number of outcomes in x divided by the number of outcomes in the sample space. And if I'm asking you to find a specific outcome, that means that there's only one of that outcome. But let's talk about the number of our sample space. Well, again, because it's continuous, there's an infinite number of outcomes. So you would end up with 1 over infinity, which if you were to take this, it would, you can't take 1 over infinity, but if you could, using something like limits, things like that, it would basically be infinitesimally small. So we'll just say that it's roughly equivalent to 0. Now let's go back to talking a little bit more about these normal distributions. If you have some number line and we consider different means, so we'll call this mu1. So this would be some normal distribution centered at mu1. You have mu2, which would be some normal distribution centered at mu2. And we have mu3, some normal distribution centered at mu3. Again, the mu, the mean, will tell you where is this normal distribution actually located. If we were to maintain mu, but change our standard deviation, so let's say that this is going to be standard deviation 1. I'm actually just going to call this an I because the mu is not going to change. What happens as my standard deviation increases? Well, it means that I have more spread. So in this case, it would mean that I'm going to have less of a peak and I'm going to decrease at a slower rate, meaning I'll have bigger tails. So this would be where sigma 2 is larger than sigma 1. And the reason the peak has to go down is because, remember that the area under this curve has to be equal to 1. So as I spread out more and more and more, it means that my peak would need to be lower to account for that. And I have fatter tails. Now, what does this actually represent? Well, again, this area under the curve represents the probability. And if you kind of think back to when we were doing the empirical rule, we had a rule about if you have a perfectly normal distribution, if I go out 1 standard deviation, it accounts for 68% of the data. If I go out 2 standard deviations, it accounts for 95% of the data. If I go out 3 standard deviations, it accounts for 99.7% of the data. Well, if this first one has a standard deviation of 1, let's say that this is plus or minus 1 standard deviation. So this area represents where 68% of the data is. The second distribution, let's say that 1 standard deviation is this far out. So what's happening now is that I have a much bigger area accounting for, or a much wider range of x values being represented for this same area of 68% of the data. So while this one, your x values for 1 standard deviation would only be from here to here, the second one with a higher standard deviation would have x values from here to here to account for 68% of the data, meaning that you're going to have more spread in your data. Let's say that this represents the height of high schoolers. Well, if I have a standard deviation of 2 inches, that means that I would, and let's say that the average height is 59 inches. That means that I would expect 68% of the people to fall within 57 and 71 inches. If I had my standard deviation is something like 4 inches, that means that 68% of the people who I would measure, I would expect to fall within 55 inches to 73 inches. More spread. You're going to have more people who are further below. You're going to have more people who are higher above. Also, because these tails are fatter, that means more of the extreme values will occur. And this actually can have major implications whenever you're using any sort of probabilities. An example of this would be if you keep up with Wall Street, there's these things called martingales, which are like normal distributions, but they have fatter tails. It means that these outcomes further out in the extremes are more likely. So that's why you might see so many once in a lifetime or once every 100-year events happen more often. And it's because they actually have fatter tails representing that there's more likelihood of these extreme values. So for a normal distribution, maybe it's a very small outcome, very small likelihood. Whereas with the fatter tails, it's still fairly small, but it's much more common. It might be double, triple the probability of something occurring. When I showed you how you actually find probabilities using integration for a continuous probability distribution, let's say you're going from A to B, f of x dx. Well, what is this function that describes our Gaussian curve? Well, our f of x, based on some mu and sigma, is just going to be 1 over 2 pi, square root of 2 pi sigma exponential of negative x minus mu squared over 2 sigma. Now, for this class, we're not going to be expecting you to calculate this way, but this is actually what that function, that f of x, would be if you wanted to solve this using integration. This would give you the probability for any area A to B based on your normal distribution, which is reliant on 2 factors: mu, where the distribution is actually centered, and sigma, how spread out is that distribution. So when we have our normal distribution, we talked about the fact that it's symmetric. This means that if I were to slice it right where the mean is, I have a mirror image to the left and to the right. And the left accounts for 50% of the data. The right also accounts for 50% of the data. The area under this entire curve will be equal to 1, meaning that this side of the graph is 0.5. This side of the graph is also 0.5. This means that something being below the mean is just as likely as something being above the mean. It's 0.5 probability of falling above and below. And any amount that we go from the mean is also equally likely as the other direction, meaning that if I, just like with our empirical rule, if I go out some amount to the left, so mu minus, I don't know, let's say that it's sigma, but it could be some other value, and I go out to the right, mu plus sigma, the area to the left and to the right of the mean mu would be equal with each other. And this is going to be tremendously useful whenever we start calculating probabilities using our tables, because we're going to know by the fact that if I have anything happening on the left, I can visualize it as the mirror image of what's on the right. An example of this might be if I'm looking at the probability to the right of some point on the left, I could flip this around the mean right here, and this would be equal to everything to the left of that positive value. Let's call this A. So this symmetry is actually going to be extremely important when we're looking at our normal distribution probabilities. Now, before we finish up section 5.1, I just want to talk about how do you actually know if your data is normally distributed? Well, there's a couple different methods. The first is that you can use a histogram. So a normal distribution's histogram should be roughly bell-shaped, right? And we looked at this previously. If I have a binomial distribution and I graph it out and it looks something like this, I could kind of visualize that I could overlay a line, and if it looks bell-shaped and symmetric, then it kind of looks like it may be a normal distribution, or at least it might be very close to a normal distribution. Method 2 is you can look for outliers. A normal distribution should have no more than one outlier. And the third method is what's called a quantile-quantile plot, or a QQ plot. So if the given data point lies close to a straight line on this QQ plot, then the data is normally distributed. So the way that a QQ plot works is you have your actual values on one axis, and you have the theoretical values that you would have if it was normally distributed, based on the normal distribution that you're testing it against. And then there's this line which represents what it would be if they were perfectly lined up, meaning that if I have this value here, it would be the same if I had this normal distribution. So then if you were to plot your data on this axis, on this line, if you have data that roughly looks pretty straight, looks like it follows this straight line, then this indicates that it's likely from a normal distribution. And there's going to be some amount of spread where it might be something like this, where if you have something within these sort of boundaries, then it's expected that this actually looks like it does appear to be normal. What might indicate that you don't have a normal distribution would be something like if you have data that does something like this, or maybe it curves. And looking at this, if I tried to draw a straight line to describe these orange dots, notice that there's no straight line that really represents it. Whereas with the pink dots, I could draw a straight line. Maybe it's not perfectly this line, but maybe it could be something like this. Then this does appear to have some normal distribution. And it might be that the reason it doesn't line up perfectly with this line is maybe my normal distribution that I'm testing against is slightly off. So QQ plot is actually used quite a bit when testing to see if something's normally distributed. In fact, in the real world, what I would do a lot of times when I get data is I would use something like R to check very quickly what the histogram of the data looks like and do a quick QQ plot to determine whether they look normal. If they do appear to be normal, I might then do some sort of mathematical test to see whether it seems to indicate they are, something like a Shapiro-Wilks test or something like that. And if I see something that's pretty obviously not normal, for example, like a curve in the data or something like that, then this might be an indication that my data is in fact not normal, and I might need to take that into account whenever I'm doing whatever sort of modeling that I'm looking to do. Because remember, every model that we use in statistics has some underlying assumptions. And if one of the underlying assumptions is that your data is normally distributed, well then you need to check whether that data is in fact normally distributed. Now, we do actually talk later on about why this oftentimes is the case, but you still should always be checking it. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.